operational amplifiers. Bam. And I have, as promised, 6 of these things. Let's go through them, and I will look at them and talk about them simultaneously. Here I go. Operational amplifiers number 1. Here was the whole point. We realized in the transistor unit that you could use transistors to amplify signals. That's one of the important properties of transistors. You can use a transistor as a switch to turn things off and on, but you can also get amplification, more voltage or more current using transistors. But every transistor circuit we build is a little bit crappy. So the electrical engineers got together and they figured out what is the best possible transistor circuit that you could build that would act as an amplifier. And here it is. This circuit diagram is very, very complicated, is an operational amplifier. Specifically, it's the 741 operational amplifier, which was originally designed and produced in 1971, just like yours truly. I also was designed and produced in 1971. Anywho, fun fact. Anyway, so that is what an operational amplifier looks like on the inside. So inside the guts of those little triangles that we've been playing with for the last 6 assignments, inside their guts is all of this nonsense that I don't have to worry about anymore because it's built in. So, op-amp basics, all right? So my first question is, an op-amp fundamentally is what? Well, I have to go looking for that. And I meant to do this in the student view, so I wouldn't immediately have the answers. It's too easy for me here. An op-amp is fundamentally a voltage amplifying device. So the answer is voltage amplifying device, and where is it? It's right here. An op-amp is fundamentally a voltage amplifying device. We have classmates here who say that the reading is not their thing. But there's the question, there's the answer. So let's sort of get them together there. An op-amp is fundamentally a voltage amplifying device. The op-amp is, I have to do a little shifting around here because on this, I still have little issues sometimes. Question number 2, the op-amp is generalized as its own component because all 3 of these things are true. Op-amps are extremely useful because they're so well designed, and there's all those little components and whatnot. So we stick all those little components in one package, and then we don't have to worry about all the parts. Always has the same construction, that's true. So you can just pack it up and be done with it. You never have to fiddle with what's going on inside. And so all of that is talked about here in the little texty part. The terminal on the op-amp labeled with a negative is the inverting input. Now, if I scroll down here, here's my op-amp. It's represented by a triangle in our I circuit. They don't actually look like triangles when you use them in a Tinkercad circuit in real life. They don't actually look like triangles. Coming up very soon, we're going to start talking about what a op-amp package actually looks like, but they don't look like triangles. But there's the one that's labeled with a negative. I wish the negative was a little bit longer because it kind of looks kind of like a dot. But that is the inverting input, and so that's what it's labeled right there. The op-amp has 2 inputs because it functions as a difference amplifier. The 2 inputs are provided because the op-amp is almost always operating as a difference amplifier. Now, a difference amplifier is a thing that I built with transistors. We built a transistor circuit that was a difference amplifier. We have 2 inputs into the amplifier. We have 2 inputs into the amplifier, and if those inputs are the same, the amplifier doesn't amplify anything because what it amplifies is the difference between 2 signals. And in that transistor circuit, we shifted one of the signals by 180 degrees so that they would be completely different one from the other, creating a difference. An inverting amplifier is the next stimulus here, and so I move on to those things. Actually, we're expected to build this thing in I circuit. So I probably should maybe switch to I circuit to build this thing, I guess. Or is it easy enough? Let's see. I'll decide whether I actually have to build it. You actually have to build it because it's required. You can tell it says build this inverting amplifier. But here's my inverting amplifier here. The reason why it's called inverting is because I'm using the inverted input. That's true. But also, If I give a positive input, I get a negative output. In this context, that's what inversion means. So I'm going to check the voltage output of this thing and check to see what it is. So if you actually build it, you're going to find that the voltage output of this thing is 0.999 volts. Is that right, or did we change that? Is that the correct one? I feel like maybe it changed, but there it is now. 0.999 volts is how that's going to turn out. And the input voltage is 100 millivolts, and the output voltage is nearly a volt. So I put a little voltage in, and I got a lot of voltage out. In fact, I got 10 times the voltage out that I put in. It's amplifying. That's the point. It amplifies. And the answers are negative because it amplifies and it inverts. It's an inverting amplifier. So we're going to take this DC source and we're going to replace it with an AC source, and we're going to find out that it amplifies AC sources as well as it amplifies DC sources. That's kind of the point of this question. Our op amps work for DC, and they also work for AC. That works out really well for, oh, shoot. There we go. So, and when you use the scope with an AC signal in, it turns out to be a 100 millivolt swing on the input, because I asked you here to make the AC source 50 millivolts. So that means it goes 50 millivolts positive, 50 millivolts negative. That means the full swing is 100 millivolts. So I could answer that one without even building the circuit. When you scope it, you find out that you get the peak to peak of the output is, again, 0.999. The same answer as the answer to number 5, because it's the same amplification. It's not negative because the peak to peak is never negative. Peak to peak is never reported as a negative number because the signal is sometimes positive, sometimes negative. But if you look closely and compare the input signal and the output signal, what you would find is that when the input signal is positive, the output signal is negative. And when the input signal is negative, the output signal is positive. And that's not surprising because, again, it is inverting. I have to, pardon me for just a second. I have to change back to my other mask. This is not working for me. All right, this will be a little better. So you've built this thing and you drag and drop the screenshot of it there. There's no alterations to do to it. No, there is actually. It says modify it so it does not amplify. Well, if I read down here, what I learn is that the amplification, which is also known as the gain, it's written right here in this paragraph, the gain of an op amp, or of an inverting amplifier specifically, is the ratio of these two resistors, the resistor over the top and the resistor at the input. That's where the gain comes from. So if these two resistors were equal to each other, then the inverter produces no gain. You say, well, that's useless. Actually not. Sometimes an inverter is useful. Sometimes you want to take a positive signal and turn it negative, in which case you can build an inverting amplifier and just have it not amplify. So I could make this one 10K and this one 10K, and then that would be not amplifying, and then I can upload that. Question 9, non-inverting amplifier now. So my output of the non-inverting amplifier is going to be positive because it doesn't invert the signal. So when I put 100 millivolts in, I'm going to get a positive signal out. Notice that instead of getting slightly less than 10 times amplification, I get slightly more than 10 times amplification. Instead of getting slightly less, I get slightly more. The reason why, and I'm going to cheat and scroll ahead, is that the way that the gain of this amplifier is calculated is a little bit different. Instead of just being the one resistor divided by the other, in this case, the resistor that goes under and the resistor going to ground, instead of it just being the ratio of those resistors, it's the ratio of those resistors plus 1. So when this resistor is 10 times this resistor, I get a gain of 10 plus 1, which is 11, which is why that works out to 1.01 volts. Hey, Drew, you still with us?
Taking down notes, Mr. Shively.
Are you enjoying yourself?
Of course.
This is not really the practical stuff, but in electronics right now, we're starting to get towards circuits that you can use to take over the world. We're like on the verge of it.
Oh, yeah? You're going to make some AIs and stuff?
Absolutely. So, question 10. Oh. What? Oh, no. Yeah. I'm sorry. I got lost in what I was doing. So now I'm on to the next stimulus, the AC non-inverting amplifier. When I build an AC non-inverting amplifier, you say, well, you just change the source from DC to AC like you did the first time. Yes. I can just change from a battery to an AC source. Yes, I can do that. But I also add this capacitor and this resistor for filtering purposes. Because I know if I put a capacitor and if I combine a capacitor and a resistor like this, I get filtering, which happens. So you build this thing and then you measure the peak to peak of the output, give it a try. You're going to find out that that peak to peak is in fact 5 millivolts. The input is 1 millivolt peak to peak. The output is 5 millivolts peak to peak. So the output of this thing should be 10 times larger. This thing's not doing what it should. I should get 10 millivolts of output because I got 1 millivolt of input. I should get 10 millivolts of output. It's designed to have a gain of 10, but I only got 5. What's happening? What's happening is my frequency of the source is below the breakpoint. This thing's got a high pass filter on the input. So it's only going to give me my amplification when I've got the frequency right. So we juice the frequency and then we find that we get 10 millivolts on the scope. Why would I want to do that? Well, maybe in a bunch of signal that I'm sending into my circuitry, I have signals that I want to amplify, the good stuff, but I don't want to amplify the bad stuff. For example, in an audio system, things get plugged in. I don't know if you've ever been to a live show. Things get plugged in, they go, that's bad signal. You don't want that. You don't want your amplifier to amplify the undesirable thing. So your amplifier very often would have some sort of filtering on it, maybe even band pass, where the high and low frequencies are removed and only the desirable band is passed through. A little bit later on, we're going to have an op-amp circuit that acts as a band pass filter and only allows a narrow range of frequencies to pass through. It turns out that using op-amps to build filters is better than the way that we built filters with just passive components, resistors and capacitors. Anyway, so I build that thing and I upload it and I get my points, and that is the end of OpAmps number 1. All of the points acquired. So I'll go back to my list here, and I'm just going to keep on trucking and go right on to OpAmp number 2, the summing amplifier. It's a funny, I guess it's very difficult to appreciate that when you have op-amps and they're doing these things, it's starting to give you new possibilities for modifying signals to suit your purposes. And the trouble is, for the person new to electronics, is you don't know what's possible, so you don't know what to imagine is possible, so it's difficult to appreciate the advantages. I'll see if I can give you some insight as we go through this. OpAmps 2, the summing amplifier. It's another type of op-amp configuration used to combine the voltages or 2 or more inputs into a single output. Notice I've just got my triangle here. That's all. Same thing. I'm not using a different op-amp. It's the same op-amp. It's the same one I drag off all the time. But now I'm inputting 2 signals into it. Notice that I've got resistance that comes over the top, and the non-inverting input is grounded. So this is working just like an inverting amplifier. It's just got 2 inputs instead of 1. The thing about this is, every time you modify a circuit slightly in electronics, it gets a new name, like it's a whole new thing. But it's really not. An inverting amplifier with just two inputs. A really fascinating thing about it that's deep and difficult to understand is that this input at 2 millivolts only cares about the 1 kilo ohm resistor and cannot see, in giant air quotes, the 2 kilo ohm resistor. So these two inputs are completely independent of each other. They don't mess with each other. And the reason why is the golden rule of op amps. It's funny that I didn't have any questions in the first op amp assignment about the golden rule. There's a thing that's called the golden rules of operational amplifiers. There are two. The first is an operational amplifier draws no current. No current goes into an operational amplifier. The current, if I was to click in I circuit right outside that negative terminal there, the inverting input, the current would read 0. An operational amplifier draws no current. The second golden rule is a little bit more tricky. The output of an op amp is whatever it needs to be to make the difference between the two inputs 0. That is a more complicated idea and one that you need to spend time and experience with before you really get nailed down. At any rate, question number 1. A summing amplifier is constructed from an inverting amplifier with more input resistors added. I just have an input with a resistor, and instead of there being one resistor, there's 2. And the other 3 choices here are nonsense. An op amp never has 2 outputs. And it always has 2 different inputs. So it's not 2 inverting inputs. It's all garbage. The only true answer is that there are now 2 resistors at the input instead of 1. Each input sees only their own input resistor. Well, I just said that. That's a true thing. And it's written in here. Yeah. It says right here, we can also add more inputs if required as each individual input sees. C apostrophe S? C is like, what's the English on that? S-E-E-S. Why did I put an apostrophe? No, I got quotes and then I typed apostrophe S. I don't think that's, I lost my mind. Anyway, there's the answer. The answer's true to number 2. You just had to read it out of it. You just had to read the thing. And some of us, don't read. So DC offset on purpose. If I take our AC source in I circuit and I just drop it down and I scope the output of that AC source, what I see is a sine wave that goes up and down. And what I never noticed before is that the center line that goes down the middle of that sine wave, like right down the middle of the up parts and the down parts, that center line is at 0 volts. And there was some assignment earlier on in foundations or transistors, I can't remember which, where we realized that signal had been shifted up or down. This is called DC offset, because it's offset from 0, a little above 0 or below 0. So you build this thing, and this potentiometer is centered. Notice that it's right in the middle between plus 15 volts and minus 15 volts, and it's centered there. Imagine it's like a knob, because that's what a potentiometer is, or actually I should say that's what knobs are. They're potentiometers, and it's a knob and it's centered. And so you run this thing and you looked at the scope trace, and it goes up and it goes down and it goes right through 0. 0 is the center line, and maybe you never looked at it before on the scope, but that line is labeled as 0. So it goes right through the center voltage, and the center voltage is 0. But when you turn the knob, how do the input and output signals compare? They're identical, but the output is inverted. This is what I was talking about. This is an inverting amplifier. So when the input is positive, that is when the input signal goes up, the output signal goes down. They're opposite of each other because it's inverting the input signal. It's an inverting amplifier. Maybe that's desirable, maybe it's not, but that's not the issue here. But it was an opportunity for me to say, hey, look at them both. So they are identical, but the output is inverted. It's an inverting amplifier. And then there's some nonsense choices there. Number 5, turn the pot to the 3/4 position. Now, I don't know why the potentiometers work this way, but you know that an eye circuit, when you go into the potentiometer, its position, like the slider position, is between 0 and 999. And when you get to 1,000, it goes back to 1. I don't know what that means, and I don't know why it says an M next to it. I guess milli. I don't know why it's not expressed as a percent. But if I want to put a pot to the 3/4 position, then I set the pot position to 750 M in the simulation, and I check the DC offset. Now it doesn't go through 0. It goes through 4.4. So the whole signal is shifted upward. And the line that goes through the middle of it is 4.4. Luckily, on the scope window, there is a DC offset like indicator, like it tells you what that value is, and you'll find that it's 4.4. And we had previously ignored it because everything that we've done so far, it was 0. Turn the pot to the 1/4 position. Well, 1/4 is 25%, is 250 M on the pot selection. It's negative 4.4. We shifted it up by turning the pot one way. We turn the pot the other way, shifts it down. Same distance, negative 4.4. And I don't know why it like drifted through my head right now, but this is sort of the beauty of Scheidele's electronics and the way that we do electronics, because calculating that is horrendously difficult to do, like mathematically proving that it's so. But iCircuit lets us avoid all the mathematics. You just build the simulation and you simulate the thing instead of doing all of the electrical engineering. Somewhere at a university, there's a senior level electrical engineer who's being given problems like this that they have to work out with a pencil and paper. And we do it with circuit simulation, which is pretty damn cool. And what makes it possible for us to solve fancier problems than we otherwise would. Turn the pot to maximum. And that'll tell us the maximum DC offset we can get. We can get 10 volts out of this thing. And that's pretty cool. And modify the circuit so that the maximum DC offset is 15 volts. How am I going to fix it so that the DC offset changes? Well, you're going to find that if you mess with this 15K resistor, you can change the maximum DC offset. So leave the thing set to full power, and then just tweak that resistor there until the maximum DC offset gets up to 15 volts. And then you screenshot that and turn it in. And that is the end of OpAmps number 2. Looking at foundations. OpAmps number 3, the differential amplifier, which is what an op-amp is by default anyway. So this operational amplifier exercise is all about learning about what op-amps do sort of by default. So now we're going to use both inputs, and we're not going to amplify the inverting input. We're not going to amplify the non-inverting input. We're going to amplify the difference between the two. That's why it's called a difference amplifier or a differential amplifier. So here's how it gets constructed. Notice that I have an input I2 that's going into the non-inverting input, and I have an input I1 that's going into the inverting input. So there are two inputs. We're using both inputs. In our previous op-amp circuits, we like grounded one of them or set one of them to a fixed voltage, but here we're going to use both inputs, right? The inputs of the operational amplifier are called inverting and non-inverting. I just wanted to reestablish it. That first question there is like a free point. Inverting and non-inverting. The inputs on an op-amp may be used simultaneously. That's what I'm doing here. By the way, you might look at question 2 and say, well, how was I supposed to know? Well, it's written in here somewhere. I just have to read this paragraph and see that it's true. But that's what that's what I'm doing. I'm going to use both of those simultaneously. Question 3. Difference amplifier is so called because it amplifies the difference. Well, I think I've emphasized that many times now, that that's what the difference amplifier does. Now, here's a thing that happens. I drag math into it. I just alluded to the fact that if you're trying to work these things out, electrical engineers have to do lots and lots of math with equations, very often differential equations, math on higher levels than is taught in high school, university math. But every once in a while, I like to show you a little bit of what the math is going on behind the scenes. It's sort of unavoidable if I want to give students of electronics a feeling of how electronics really is. So here, the math. I've got currents running in I1 and I2. They're the currents. If I go back to this, that's I1 and I2. And IF is the feedback current that flows over the top. Now, typically when you use an operational amplifier in an application like an inverting amplifier, the current in R3 would actually be back toward the non-inverting input. That's called positive feedback. This feedback is going to the output. It's called negative feedback. So IF refers to that there. Here's how I calculate those currents based on the voltages that I get. And A and B are called a summing point because the voltage at A and the voltage at B will be equal to each other because that's what an op-amp does. An op-amp makes the output of the op-amp is whatever it needs to be to make A and B equal to each other. So when I write that, that's sort of like one of the golden rules of op-amps. So I can calculate VB, and then VB is equal to VA. And if I set this equal to 0, then the output voltage is going to be found this way. So I'm just giving the math here, but then over here and then I'm just trying to find the output voltage. So over here on the actual questions, oh, am I going to have to do all this math? No, it turns out not the case. The output of the differential amplifier is found using the principle of superposition. That says somewhere. I'm like afraid of myself. Oh, superposition. There it is. And that's the answer. It's important, I guess, to be like a little bit brave, not to freak out, because I don't want to show you like Lego electronics. I want to show you real electronics. And so, funny, the other answers here are great. Moments, the principle of moments. The principle of moments. That's rotation, isn't it, Michelle? That's the principle of moments. It's also a 1980s album by former Led Zeppelin frontman Robert Plant. Anyway, general relativity, special relativity, average voltages and Ohm's law, all that's garbage. The principle of superposition is the correct answer there. The term unity gain means that the gain is 1. That's what unity means. Unity means 1. And so unity gain means the gain is 1, which means the signal is unamplified, which means the signal is unchanged. That's what unity gain means. It's going to be in here in the text somewhere. Will be exactly 1 or unity. Will become unity gain differential amplifier if all the resistors are the same. Then the output expression would simply be V out equals V2 minus V1. And doesn't really say that the signals won't be changed, but the signal is unchanged at unity gain. So maybe that was a question that you dropped. We picked that one up now. What would V out be if V2 was 5 and V1 is 5? Well, here's the equation for V out. So all I have to do is plug in V2 and V1. So I put in V2 is 5 minus V1 is 5. 5 minus 5 is 0. The answer is 0. 5 minus 5 is 0. The answer is 0, quite simply. What would be V out if V2 was 10 and V1 was 5, but R1 and R2 are equal? So this is 10 minus 5 is 5. And if R3 and R1 are equal to each other, then R3 divided by R1 is 1. And the output would be 5 volts. Just using that equation and plugging in some numbers. And then a final challenge there. What would V out be if V2 is 10, V1 is 5, but R3 is twice R1? Well, then this would be 10 minus 5 is 5 times, if this is double what this is, this will be 2. So it's 2 times 5 is 10. So a very little bit of algebra and arithmetic there just to ruin your day. not for any education purpose, but just to make the whole thing work out terrible, that works out to be 10 volts. So it's possible for an engineer who's building a difference amplifier to make choices about resistors and the construction of the thing to get it to work out the way that they want. Here are some applications. This is a Wheatstone bridge as being here. And so it's there's just a lot of reading that goes on here. And a lot of reading because there's a lot to say. But somewhere in here, differential amplifiers can add or subtract, which is pretty cool. Here's a thing about photoconductive cells that are resistors that are affected by light. Now, the reason why I wanted to bring that into this, resistors that are affected by light, is because when you learn enough electronics that you want to start building things that are useful. Photosensitive circuits are fun to do. Like if you want to make a circuit that activates when the lights get turned on or when the lights get turned off or something like that. And many of us have that at our homes. There's a little sensor outside, and when the sun goes down, the light comes on. When the sun comes up, the light goes off for safety reasons and whatnot. So those are devices where their resistance depends on the amount of light that is present. The standard differential amplifier circuit now becomes a differential voltage comparator by comparing one input to another. There's nothing to that except language. When we encounter new bits of electronics, there's new language that goes into it, new vocabulary that we need to learn. A differential amplifier is also used as a comparator because it compares one input to another. So here is a 2-input differential amplifier just to give it a try. R1, R2, R4, and R3. And I had a little trouble with the defaults. I wanted all of these resistors to be defaults, which I think is 1K in I circuit. Well, when the resistors are default and 1K in I circuit, the output of this thing is going to be 0 volts. Because the thing is so symmetric, there's no difference between the inputs, and a differential amplifier amplifies the difference. If there's no difference, then there's going to be no output. Double V2, and it was probably 5 volts to start off with, so now it's 10 volts. And then check the voltage output. Well, now it's 5 volts because the difference between them is 5 volts, and R1 and R3 are equal. So it's going to be unity gain. It's not going to amplify the output. But it is going to give me the difference between the two. If this is 5 and this is 10, the difference is 5, and it gives me the difference. I'm going to put, instead, this top voltage, I'll make the top voltage 10 volts and the bottom voltage 5 volts. And when I do that, I'm still calculating the difference between the bottom one and the top one. But now when I subtract, I'm subtracting in the reverse order. So it's 5 minus 10 is negative 5. And so what I get on the output is a negative number. Because I reversed the direction of the thing, I've reversed the subtraction, and I get a negative number at the output. So you build this thing. And there's a little bit of a challenge here. So I want to make this differential amplifier. What do I want it to do? For which V1, V2, R1, and R3 are all different, but the output is 15 volts. Remember that R2 equals R1 and R3 equals R4. So you just pick some values and you build the thing. And then you check your output and, oh, it's not right. Well, if your output is smaller than what you want, if it's smaller than 15 volts, then increasing R3 and just amplify until you get where you want to be. So you choose values, bing, 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 build it, and then just juice R3 until you get an output. And then you take a screenshot of that and you upload it. And that is the end of OPA3. How much time do I have? I have not memorized this bell schedule. It's at 40? Thank you. So I have time to get number 4 done. So I'm going to talk about 4. And then tomorrow I'll get 5 and 6. And then I can start assigning some more. which would be really great. Operational amplifier 4. Is Drew still with us?
I'm here.
Drew, you got to get this eye circuit.
Yeah, I've been taking some notes, you know.
Yeah, I do know.
It's been fun.
This is calculus, man.
Oh boys, golly gee, lots of fun.
You nerd. OPA4 calculus. No.
Do you like my background?
Oh, I should check it out on the Zoom. I've got it. What the? Oh, you.
You gonna play some checkers with me during bonus block, Mr. Shidley? I think it'd be a lot of fun.
Sure. And then
Yeah?
after that, we'll play a game of my choosing.
Does it have to do with
You
strangling me?
running through a jungle in a deserted island.
Oh boy, sounds like India.
Yes, it's going to be very like that.
Uh-huh.
Except I'll be speaking with a British accent. I got to do this. Yeah, that was dark. Now they see what you've done. Now I got to go through and edit that out. Just kidding, Drew.
No hard feelings.
OpAmps1 calculus. Nothing but love, Drew. Nothing but love. Previous activity circuits. Oh, man. Feedback and nonsense like that. Now we're going to replace the over-the-top resistor with a capacitor. And that, as it happens, radically changes the behavior of our operational amplifier type circuit. This thing that I have right here, the integrator, look, it's got a resistor on the input. The non-inverting input is grounded, but instead of having a resistor over the top, it has a capacitor over the top. And that is, you would not be surprised, is going to very, very dramatically change its behavior. First of all, I know that when I get a resistor and a capacitor together, I get this sort of curved behavior, curving up as the capacitor charges, or exponentially going down as the capacitor discharges. So the very nature of RC circuits is like this rise and fall timing sort of thing. And so we're going to build ourselves an integrator. An integrator differs from the inverting amplifier in that there's a capacitor on the feedback path. There's a capacitor there instead of a resistor. That's the difference. When a voltage is first applied to the input of an integrating amplifier, when a voltage is first applied to the input of an integrating amplifier, the uncharged capacitor has very little resistance. A capacitor, when it's uncharged, is perfectly happy to be charged. We've been over this before when we first did passive high pass and low pass filters. An uncharged capacitor is perfectly happy to be charged. And so it offers very, very little resistance to the flow of current. So that's an answer that I might have gotten without reading all the muckety-muck here if I was just on top of my electronics. Long after a voltage is applied, the charged capacitor has what? Oh, my answer key's wrong. Nobody said anything. I'm looking at you, Michelle. When I first apply a voltage, the input of the integrating amplifier, the charged capacitor has very little resistance is the answer. It has very high resistance. It's the opposite. The answer to 3 is the opposite of answer number 2. The answer should be the charged capacitor has very high resistance. Now I got to go in here and I need to change the answer key. Very high resistance. Wow. I think I just got confused because it's the same question at a later time. Very high resistance. Good, I fixed that. Now, when an op amp is operating at saturation, that means the output is at the high or low rail voltage. The rail voltage means the voltage that you supply to the op amp. It's funny, it was a while before I thought about it this way, but when you have an op amp, you actually sort of have to plug it in. An op amp has to be powered. And in our simulation, just like in this diagram here, it doesn't show the voltage connections. But an op amp has to be powered to work. And the maximum possible output voltage that an op amp can have is the maximum voltage that you supply it with. The maximum possible output that it can have is the maximum voltage that you supply it with. Right? I was trying to think of an analogy for that and I failed. My terrible analogy was going to be, how many M&Ms can you eat? And your answer would be, how many are you going to give me? And you say, besides that doesn't work, because if you give me enough M&Ms, then I will either explode or vomit. Well, yeah, if I put too much voltage on my op amp, it will either explode or vomit. So I think maybe it's a perfect analogy. I'm not good at analogies. Anyway, the output is the higher low rail voltage. That's what goes on. If the integrator's input signal is a square, the output is a sawtooth. We can actually see that down here. If my input is a square, then the output is a sawtooth. Drew, look at that really carefully and realize that if you integrate a square, the integral is a sawtooth. I'm looking at the answer key right now. It says sawtooth on my screen.
Why is that, Mr. Shadley?
Why is what?
Why is the integral of a square a sawtooth?
Well, the integral is the area under the curve, right?
Yeah.
So imagine that I start here with the input signal, and I start adding up. Now it inverts, okay?
Mhm.
It inverts. So it'd be nice if it wasn't inverting, because then you'd see, as I add up, this gets larger and larger and larger and larger and larger. And then when it goes negative, it subtracts, and it gets smaller and smaller and smaller. They're actually inverses of each other. So seeing
I see that.
seeing the calculus here is a little bit difficult because the output signal is inverted. But integration, the calculus. And then, is this the same? No, this is a new. So here we build an integrator. Notice there's no op amp. This is called a passive integrator. And the reason why we build a passive integrator first is so we can see how bad it is when you build a circuit with a passive integrator. So you build this, and then you scope the output signal, and it looks terrible. In fact, I said here, well, that's pretty terrible, because a square wave is going in. Notice that the AC source here is set as a square wave. And the garbage that comes out of the output of this passive integrator should be a perfect, crisp triangle wave. And it's not. It's garbage. Well, that's pretty terrible. Look closely at this trace of the output, and you can see the curve of it charging and discharging the capacitor. And so all you do is you build that thing in iCircuit, and you upload it. Done. And now, there's more questions. There's more questions. What's the attenuation of the output? Well, you compare the peak to peak of the input, which is probably 10, to the peak to peak of the output, which is around 2.5-ish. I'm losing almost 3%. I'm losing about 3 millivolts. I can't remember what we set the. I don't know I guess it's 10 volts. So I'm losing about 7 volts off this thing, which is 70% of my initial signal. The signal is badly attenuated. So answer the point of the whole thing, passive integrator, bad. 70% attenuation is awful. Passive integrator, bad. Number 8, drop the frequency of the source to 1 hertz. Now you can really see it. The capacitor is charging and discharging, giving a fake graph of the integration. Not a perfect sawtooth, but a crazy risey, folly, exponential garbage festival. And if you do that and do the peak to peak of the output, you'll find that it's 2.5 volts. Remember the golden rule, grasshopper. The output of the op amp will be whatever it needs to be to make the two inputs equal. Scope the input and output of this integrator. I should actually edit this. So I mean the input and output of this active integrator. So I should edit this. I'm not changing anything, but I should make it clear of this. And I've been trying to use caps to be very clear in my questioning what it is. Or what particular circuit it is that I'm talking about. It's the active integrator. And when you do it, you'll find you'll find that it produces a lovely, lovely triangle wave. So when you take a screenshot of your scope window, by the way, there's a thing that I've noticed when people are turning in their assignments. Some people are giving me pictures of the circuit when I asked for the scope window. Sometimes I'm asking for the screenshot of the circuit itself, and sometimes I'm asking for the scope window. I'm hoping as we go forward, people will be careful to look at that and realize I don't need to see the circuit. I need to see what the circuit output looks like. Now the differentiator. I had an integrator, now I have a differentiator, and the main difference is that the capacitor and the resistor are switched. Look, I have the resistor over the top now and the capacitor on the lead-in. So I've reversed the order of those, and that's going to reverse the behavior of the thing. If I put a triangle wave in, I'm going to square wave out. It does the opposite of integration, which those who study calculus know, the opposite of integration is differentiation. There's a little multiple choice question here. The differentiator output is proportional to the rate of change of the input. That's got to be in here somewhere. It's a little bit more abstract, but those who study this kind of mathematics realize that derivatives is what it's all about, and that the rate of change of a thing in mathematics is known as a derivative. That's got to be written in here somewhere, but I'm not seeing it. Rate of change of the input. Yep, rate of change of the input. The input's voltage rate of change with respect to time. That's where that answer came from, this paragraph. This operational amplifier circuit performs. Now I'm on to the next stimulus here, building a differentiator. I'm going to do the same thing again. This is the passive differentiator. Notice there's no op amp in it. You build it, you see that it works like crap. That's the whole point of that. And then you build the fancy one. This is the active differentiator, right? So you build an active differentiator, and what do we want to do? We want to scope the input and output. It succeeds in converting a triangle. Notice the input here is a triangle wave. It takes that triangle and turns it into a square. And so I'm asking you to upload a screenshot of your scope window so I can see that you've successfully got the active differentiator to turn a triangle wave into a square, whereas the integrator turned a square into a triangle. Challenge! Wait, what? Oh my goodness. Look at that thing. This is fun because it's a circuit that I built. This is really just for fun. It's a circuit that I built that takes a triangle wave and converts it into a sine wave. Notice that there's no op amp at all in this one, because an op amp isn't necessary to produce a triangle wave, because all I have to, or to produce a sine wave, because all I have to do is take a triangle wave, which already goes up and down, up and down, up and down, and tweak it. So you build that thing. Did I even ask for a file upload? Yeah, I did. So you build that thing and then look at the scope window. I want to see that it makes a sine wave. It's tricky to build because you got to be careful. These little bits here, the wires cross over, and here they attach. So building this thing requires a bit of eye circuit skill because it's easy to mess it up and put a component in the wrong spot. What's the attenuation of this guy? 40%. That is the end of operational amplifiers 1, 2, 3, and 4. So tomorrow we meet for half an hour, and I can finish off this video by doing operational amplifiers 5 and 6.
Starting with operational amplifiers here, I'm going to go in, and here I have operational amplifiers 1 through 6. I finished off with 4 calculus there, so I'm going to go to 5 operations and explain all of this. So it's using operational amplifiers to solve math problems. Now, there's a particular math problem that I solve in this assignment, but if I arrange my operational amplifiers appropriately, as it happens, I can solve any math problem. So the first thing is this little stimulus section here called rock solid voltage. And it's a bit subtle and easy to miss, like the really cool thing about this. And that is that I have this operational amplifier here and 5 volts going into the non-inverting input. And I have the output feeding back to the inverting input. In order to build this thing, you know, when I choose an op amp by default in iCircuit, it does negative positive. Well, now there's a little, where you go on the options for that, you can swap it so it's positive negative. And I set it up like this. I have this running around underneath. What this effectively does is turns the operational amplifier into a voltage source. Here's what I mean by that. It's basically a non-inverting amplifier with 0 amplification. So the output that I get here is, well, right here actually, is exactly this input. Now this voltage source here, 5 volts, no matter what voltage it is, I mean a real voltage, like a battery, I plug a 9-volt battery to it and go into an op amp. The op amp will provide that voltage with no droop. It doesn't matter what load I put on. I'm going to get exactly 5 volts at the output, no matter what the load is. That's the advantage of using an op amp. If I take a 9-volt battery and I hook a motor to it, because of the impedance of the motor, the voltage on the battery droops. That's one of the things we talked about very, very early in the foundations unit. Well, these voltage supplies don't droop. And so the first thing that happens in this assignment is to create these 3. What we're trying to do is we're going to build a circuit that does A plus 2B plus 3C, where A, B, and C are voltages just created. Now notice that I have 10K resistors on A and C, but on B I have a 5K resistor. What that effectively does is gives me the 2B that I'm looking for. So that's how I get my factor of 2, is by reducing this resistance by half. So that I've already got my 2B, but I don't have my 3C. I'm going to do that in a more clever sort of a way. So why not use batteries? These are stiff no matter what load we put on them. The resistor of output to 5K instead of 10. That's what makes it twice. So I just mentioned that. And then here they are, A, B, and C tied into the greater circuit. Now A and B just come together here and feed into the next op amp. C also goes into the next op amp, but before it does that, it goes through an op amp that is in the inverting amplifier configuration. Here's what that does. First thing, the output of this op amp here is going to be negative. That's what gets me the negative in negative 3C. But I also want it to be multiplied by 3 to do that math. So notice that this 30K resistor is 3 times larger than this 10K resistor. Then as a result, this amplifier does 2 things. It negates, that is, it inverts the signal, and it multiplies by 3. So what I have lined up right here is A plus 2B plus negative 3C. They're all coming together at the same node. This is all effectively electrically attached. So I have A plus 2B plus negative 3C. same thing as minus 3C. And then all of that goes into this op amp, which is going to invert the signal. So this is basically my summing amplifier, the same way we learned about summing amplifiers early in op amps. I'm taking multiple inputs into the same amplifier. So here's a summing amplifier section, and then that signal comes out of the summing amplifier inverted. So I have to invert it back again. And the way that I'm going to do that is I'll use an inverting amplifier, but the resistor over the top, 10K here, is the same as this resistor, 10K. So the ratio of those resistors is 1. So what I built is an inverting amplifier that doesn't amplify. So all it does is invert. So we could talk about this thing in the future as being an inverter. So that's what's going on with this whole stimulus. And for some reason, I asked you not to panic when you looked at the circuit. So OpAmp4 amplifies 10 volts. Where's OpAmp4? See, I numbered the amplifiers, and you can do that. You don't have to do it because I did it for instructional purposes, but you can number the amplifiers in iCircuit. This is OpAmp number 4. Amplifies the 10 volt input it gets from OpAmp3 and inverts it. Because 30K over 10K is 3, the output is tripled and hence negative 3C. What is the output current of OpAmp4? Well, to know the OpAmp current, you're going to have to build the thing and click on 10K. So this is one of the questions that I have built into these assignments that just verifies that you did as I asked and you actually built the thing. If you actually build the thing and click on that output, it's going to read 4 milliamps as the output of OpAmp number 4. It's easy to get. You just click on this 10K resistor in iCircuit when the simulation's running and read what the current is. It's 4 milliamps. So it's pretty easy to get once you've built the thing together correctly. What is the output current of OpAmp number 2? Well, which is OpAmp number 2? This is OpAmp number 2. You can just click on it. Notice that it's negative 3 milliamps. Well, that first of all of the options are negative. Well, that's because the op amp is outputting a negative voltage. So I'm going to get a negative 3 milliamp current running there. It's absolutely fine that the currents, if the current is negative this way or that way, and honestly, it doesn't particularly matter what the current is, as long as the current's not so high that it causes a risk of drawing too much power on something and overheating something, blowing something up, causing a fire. It doesn't really matter what the current is. This question is just checking to see that you've actually built the circuit. And so that answer works out to be negative 3 milliamps. The outputs of 1, 2, and 4 are joined together into OpAmp 5. This is addition. When I bring the circuits together at a common junction, that's how I'm adding. That's the function of addition put in the thing. So what is the output voltage of OpAmp 5? Well, you just have to go there and look at it. But that OpAmp voltage is 50 millivolts, or sorry, microvolts, 50 microvolts. What am I expecting on the output? Well, I want A plus 2B minus 3C is what I want the output to be. So A is 5 plus 2 times B is 30 minus 3 times C. So that's minus 30. So I want 5 plus 30 minus 30. So my output voltage should be 5, but the scale is wrong. This is 5 microvolts. So a meager voltage indeed, or I'm sorry, 50 microvolts. OpAmp 5 has a 10K resistor in parallel with it, but no resistor at the input, which means we get infinite amplification. No, you don't. The maximum you get is 100,000 times amplification on the thing. So what is the output of OpAmp 5? The output of OpAmp 5 is negative 5 volts coming on the output of that. Whoops. Everything I click on is a trap. Negative 5 is, so it's not the right answer. It's inverted. And so we add an inverter to it. Adjust the input voltages here to whatever you like. It doesn't matter that they're 5 volts, 15 volts, and 10 volts. You can make them anything now. 5 volt, you could make it 2.2 volts, 3.5 volts. You could even make it negative 6 volts, 6.37215 volts, whatever. You make those values of those batteries that input the thing. No matter what you make them, the output is going to be A plus 2B minus 3C every time, even when they're decimals. And so you're encouraged here to make them all different and upload them. That's another educational strategy there, because when I look at everyone's individual circuit, I'll know that they actually build it, because everybody should have different voltages on A, B, and C. Of course, that's not what's going to happen, but it's what should happen. So we'll see how that plays out in the long run. So this is using operational amplifiers, not to amplify, but just to solve a math problem. When would it be necessary to add and subtract signals like this? Well, for example, Evan knows that very often you have multiple signal sources when you're controlling a robot, for example. And when those signal sources have to be added in specific ways, then this kind of circuitry is what you would do, and you would use op amps to do that. It's very difficult when if you haven't done a lot of hobby electronics and built things, to imagine how these things have direct applications. But in the second, well, hopefully, in the second group of operational amplifier assignments that we're going to have, you're going to see operational amplifiers that are of very specific uses, like use this when you want to accomplish this task. And that's the lucky thing about it. We now know, we're learning enough about electronics now that we can start to do real practical things with our calculations. So that's operational amplifiers number 5. And so now we go to recent history, operational amplifiers from just a little bit ago. This is OpAmp1 multi-vibrator. This is not the first time we've had a multi-vibrator circuit. We had one in the transistor unit, where we built a multi-vibrator circuit, what you would call a discrete circuit. Instead of using op amps, we actually had the transistors arranged in space with the capacitors and resistors and diodes and so forth to construct a multi-vibrator. But now that we have the op amp in its consolidated form, we can build a multi-vibrator using that microchip, which is good. Why do I need a multi-vibrator? Well, I want to be able to produce oscillations. I want to make signals that are periodic. Earlier on in our course, when you needed an AC signal, you just reach in the eye circuit, you grab an AC source and you drop it down there, and wham, you set the frequency, you set the amplitude of the thing and all that. Where does that come from? Right? If you're one who builds electronics, then you want to be able to design and build that thing from scratch. And so that's what multi-vibrators are all about. There are really 3 kinds of electronic signals that we're interested in: square waves, sawtooth waves, and sine waves. Most of the time, we've been working with sine waves. But a little later on, when we're talking about digital logic is all about circuits being on or off, but nothing in between. That's when square waves become really important. Triangle waves are probably the least useful of signals, but they do have their specific purposes, and we'll encounter those as we go. So there's a little intro to multi-vibrator basics, but this is what it's all about. You create an electronic circuit that basically has 2 ways of being. It has 2 states. When we did it with transistors, there were 2 transistors, and the transistors were coupled to capacitors. And what would happen is a capacitor would charge until a transistor was tripped, and that transistor would then drive current to the other transistor, which would trip that one and cause its capacitor to charge. So what happens is you have these transistors that are activated or not activated. They're like right on the edge, and it sort of goes back and forth in a quasi-stable sort of situation. I don't know if any of you have seen what's known as a drinking bird. But drinking bird is a fun little toy apparatus. They make it actually look like a bird. The fact that it looks like a bird is irrelevant. But you put a glass of water there, and it dips down into the water, and then it goes back again, and then it will go back and dip again. The reason why is that the other end, there's a bulb that is moistened with water that is evaporating. And through a process of absorption and evaporation, which is in a very, very close equilibrium, the drinking bird goes back and forth. Well, that's what our multivibrator does. It has two states of being that are very, very close to each other, and it can flip-flop back and forth between those two things. A system that behaves that way is called astable. You put A in front of anything, and it very often means not that, like the word atypical means not typical. So astable means never stable, not stable. Oh, that's one of the answers is astable means. Oh my gosh, I gotta fix that. I'll fix it right now. Edit a copy. That's an error of the cut and paste. I had a professor who said that all the time. This is an error of the cut and paste. Sometimes astable. What should the other bogus answer be? Never stable, sometimes astable. Wacky. That's a good choice. So I'll say done. So never stable is where I'm going to go with that. Question 2. An astable multivibrator combines an RC timing network and a voltage divider along with an operational amplifier. That information is in the text here. And where is it? RC timing network, voltage divider network. So this paragraph describes the answer to this question. An astable multivibrator combines an RC timing network and a voltage divider. Number 3 here. The multivibrator is so called because it's constantly switching between two states. That's the vibration. Anything that vibrates, it's going between two states. And that's what the multivibrator is doing, switching between one state and the other as it goes. So it's constantly switching between states. In the multivibrator circuit, the op-amp plays the role of a comparator. It's right here. In the op-amp multivibrator circuit, the op-amp works as an analog comparator. It's comparing the two signals that come in through its two inputs. In the differential amplifier, I can't remember which op-amp assignment that was, but the one that is differential amplifier, at the very end of that, we said we can describe this as a comparator because your op-amp is effectively comparing the signals that it's getting at its two inputs. A problem with op-amp comparators is that they switch uncontrollably. When they oscillate back and forth, they don't oscillate with a regular frequency. If I go into iCircuit and I grab an AC source and plop it down in the simulation, turn it on, it's going to run with an exact frequency and the waves are going to be nice and uniform. The comparator doesn't do that. It flip-flops back and forth sort of spastically, and that's no good. So what we do is we surround it with other circuit pieces that stabilize it and make it behave itself a little better. And the stabilizing circuitry is known as a Schmitt trigger. And so once again here in this stimulus section, I've given you a lot of words to read and a bit of math. This is, again, you're not required to do any of this math in order to accomplish these things. And even if you took on a challenging circuit project of your own, you would never really find yourself in a situation of doing this necessarily. This is for the electrical engineers. When we build a Schmitt trigger, first of all, you can buy a Schmitt trigger that does what you want it to off the rack and just plug it into your circuitry. But only engineers would use these equations. But I put them here for completeness. So that, you know, I want my electronics course to be complete. That's the way that it is. So the op-amp comparator circuit uses positive feedback. Positive feedback provided by the resistors. The Schmitt trigger that uses positive feedback. Here it is in the text. It appears there. Answer to question 7. Question 8, VREF will be dependent on the fraction of the output voltage fed back to the non-inverting input. Well, this is a very, very complicated statement there. Well, look at it. Here is this voltage feeding back into the non-inverting input. So this statement appears in the text, but I can also see it on the op-amp diagram here. This voltage feeds back into the positive terminal in the op-amp, which is the non-inverting terminal. Question 9, in our simulations, the saturation voltage is typically plus or minus 15 volts. And the way that I can see that, well, the way that I can see that, I'm not going to bring up iCircuit just yet because I'm not, well, what the hell, might as well. Let me just do a new share to my iCircuit. Let's see. So here I am in my iCircuit. When I grab an op-amp, here it is, the op-amp. Oops. Op-amp, kabang. When I select the op-amp and its properties, you see that the rail voltage plus or minus is set to 15 and minus 15. This is actually a little bit weird because if I go to Texas Instruments and I want to purchase from them some op-amps, they'll tell me that the operating voltages are between 0 and 12 or something like that. There are different operating voltages depending on the op-amp that you buy, depending on the application that you want to do. The number 15 here is a little weird. It always has been a little bit weird. And I think the folks at iCircuit knew that because a new addition this year, like just recently, is this version of an op-amp with rails. And you see one of the rails here is labeled green and the other one is labeled red. This is because very often real op-amps that you purchase and buy in circuits, they don't necessarily run between 15 and negative 15. They have their own voltages. And those voltages can be supplied from elsewhere in the circuit. So if I wanted to, I could stick a positive voltage on here and a ground on here, and that would be the operating voltage of my op-amp. Notice that this is not a negative voltage, this is 0. So the op-amp is operating with only positive voltage, and that's going to make this op-amp behave in strange ways. So the choice of the voltages sort of matters. It matters. But I don't know the difference between doing this and going to this op-amp and saying, well, I want the maximum to be 5 and the minimum to be 0. I'm pretty sure these two setups are equivalent. I think that maybe iCircuit is just giving folks the option to choose how they want to set it up. But I was interested to see the rails because there was a time back in the day that I wanted it to have rails and it didn't. And I was a little bit frustrated by that. So back to our multi-vibrator here. In our simulations, it calls for plus or minus 15 volts. Oh, and there's also, we did an op-amp thing here where I suggested that it was the last one. I suggested when you do that simulation that you just set it to plus 100 and minus 100 volts. That's not realistic because that will blow an op-amp up. Op-amp just burst into flames. But it made the simulation work properly. It meant that voltage was not an issue. The op-amp could operate at any voltage. That wasn't very realistic. I wonder what's going to happen when we go to Tinkers and try to build some of these in Tinkercad. I have to be honest with you and say that is going to create issues that I haven't encountered before because I myself have not tried to build those circuits in Tinkercad. So we'll be doing that soon enough. So so we're building, this stimulus here only has one thing, and that is to build the circuit in iCircuit and drag and drop it. Notice it has the rail voltages on here. So I could use that if I want. You know what? For the sake of completeness, I'm going to go ahead and actually build this thing in iCircuit and see what I get. So I'm going to put this window to the side right now and bring my iCircuit window forward so I can see what I'm doing. And then I'm going to share my iCircuit with you, and I'm going to build this thing to see what happens. I'm going to be, I'm going to do a little full disclosure right now and say that I assigned this thing without actually building it myself. So let's have a look and see what happens. So it doesn't really say here what those voltages should be. So I'm going to start out, hopefully I'll get lucky. I'm going to start out with just the regular op-amp here, and I'm going to let it run as it does by default between negative 15 and positive 15. You know, a thing that's happening here is I'm not watching my time very carefully. Oh, I'm doing great. Everything's going to be fine. And so here I go. I need to drop in a resistor over the top here. I'm going to drop in all of the resistors and actually build the structure of the circuit. And then I'm going to go around and set all the values. So for the moment, I'm just going to drop these things in without worrying about what their values are. And that is a bad idea that I just did there. I should move this off. And you can hear the trash truck out back because it's Friday and that means it's trash day and I didn't take out the trash. Because in my household, there are two people who could potentially take the trash out and one of them is a cat. So the trash did not get taken out and I guess that's just the way it goes. I need a potentiometer. I'm going to drop this potentiometer here, and the one in the diagram is flipped over the other way, but I can flip this. I can flip this potentiometer. It's possible. I can just turn it around like that. Good. And I'm going to angle it like this, and then I'm going to take this potentiometer, and I'm going to go like this, and I'm going to go up here like this, and then I'm going to go like this, and I'm going to connect it there. And that's doing great. And that potentiometer has a resistor above and a resistor below. They fit in real nice. That's cute. And then everything's lining up really nice so that this can go right through here. Woo! Look at that. Everything turns red. That's why I don't like to work with the simulator on. It's upsetting. So this is going to come down here like this.
Mr. Charlie, I don't think we can see the screen for ISO.
Oh, yeah. I forgot to change my share. Thanks for saying. Update on what's happening. Look. So I flip this around. And now I'm going to set some values. This is 0.1 micro. So 0.1 microcoulombs or microcoulombs, sorry, microfarads. That was silly. Microcoulombs, it's not even a thing. Well, coulombs are a thing, it's a unit of charge. And this is a 43K resistor, which is actually a kind of resistor that is common. You find those laying around the laboratory. Here I have a 100K. Like that. And here this is 100K. I wonder if it says anywhere in the description what the maximum value of the pot is. Yeah. So it's saying the pot is 100K. I'm going to go ahead and assume that that means that's when the pot is centered. So if I want the pot to be 100K when it's centered, I'm going to make the pot 200K so that the minimum value is 0, the maximum value is 200K, and the centered value is 100K. That seems to be a sensible way to react to that. So now I've built this thing the way it looks there. All I have to do is see what happens. So I'm going to go ahead and start the simulator, and it seems deader than Julius Caesar. When I click on this, if I scope the output voltage, it is in fact dead. Absolutely dead. 0 voltage. So is there something that I've done in building the thing? These voltages, kilohertz, is it a frequency, a bandwidth thing? So I'll make that 10K and zippy, it starts to recalculate, but it still calculates to 0. So what have I done? 100K, 100K, oh, 10K, the bottom resistor was 10K, not 100. So I look around to see if I've made mistakes, and sure enough, I have. I'm going to turn off the simulator, reboot it. It still goes to 0. I'm actually not surprised by that. I would have been really impressed if that resistor had been the problem. This is 43K, and then here's this and this, and
Try adding a ground to the resistor at the bottom.
oh, there's supposed to be a ground. Thank you. I didn't even see the ground on the diagram because it's all squished there. Oh, there we go. What a champion. Look at that. That's beautiful. Look at the RMS of the thing. is 15 volts. The peak to peak is 30 volts. So this thing is doing the full swing of the op amp. My op amp goes between plus 15 and minus 15. And so I get a full peak to peak of 30 volts out of this thing. This is smashing. The frequency of the thing is 156 hertz. The question is, what does the potentiometer do? Well, let me select the potentiometer and change the potentiometer position. I'll put it to 3/4 by setting it to 750. How does that change the output of this thing? I guess I have to restart it. It didn't change the frequency, didn't change the peak to peak, didn't change the RMS. It did not change this circuit in any way, shape, or form. Oh, I didn't restart. Man, I didn't restart my thing. So it adjusts the frequency. The potentiometer changes the frequency of the thing. Let me go to frequencies. So currently, with the potentiometer at this position, it's running at 100.71 hertz, right? Looking at the frequencies there. Now, if I go into this potentiometer and change it, I'm going to rack the potentiometer down to the 1/4 position, 250, and I see that the frequency of the thing is now 294 hertz. So what the potentiometer is, a knob that allows me to adjust the frequency of this very excellent square wave oscillator. And it shows me a lovely, lovely square wave. Tremendous. OpAmp as a multi-vibrator circuit. The next thing that happened was I went down here and I created this very elaborate op-amp scenario. The output on this is a triangle wave and a square wave. This thing produces a square wave and a triangle wave both. It's pretty hot. And I wanted to ask questions about it, but I just got it working in class the other day. So there were no questions associated with this thing. But I suggest that you build it because it is a fantastic circuit project, one for the record books. So I now have gone through not the dashboard. I'm going to go to the dashboard. I have gone through all of the op-amp assignments. So as I said, my next steps going forward is I will go in, I will pull off my laptop yesterday's video and this video. I will edit them together in Camtasia, if you're curious about that. I'll edit them together and then I will post them as a video here. You know what? I will post them to YouTube and then I will link to the YouTube here on our Canvas page. And then I will select upload to PowerSchool all of those op-amp assignments. And so Monday, in a sense, is starting fresh with the second half of our operational amplifiers